So let's take a look at a 7-kilogram bowling ball. That's and that's a good size bowling ball. I only bowl with the 10-pounders, but you can, like 16. That's about a 16-pound bowling ball right there. And so it's rolling down the alley at 2 meters per second. And now maybe it's going to hit a pin or something like that. It's going to receive an impulse. Something's going to push on it for a very brief period of time. And that's going to change the velocity and therefore change the momentum of the bowling ball. So we want to look at that. So we've got two different impulses represented by this graph and this graph. So for each impulse shown in the graphs, find the resulting speed and direction of the motion of the bowling ball. So let's do, well, here's what's given about the bowling ball. Let's draw a little sketch. Always good to draw a little sketch. Here's the floor. And here's the bowling ball. Put 3 little holes in it if you want. Okay. And it's moving. It's got a velocity of 2 meters per second. We'll say that that's the initial velocity. And of course we know what its mass is. It's 7.0 kilograms. So now what are we trying to find? Well, for part A, we have impulse A. We also have, these graphs as given. I'm not going to redraw them. For, given graph A, we want to find the final velocity of the bowling ball. Now it says speed and direction. That's the total velocity vector they're looking for. And for part B, well, we have graph B, and we want to know the final velocity there. Same thing. Well, let's solve it. Well, taking a look let's do A first. Look at this impulse. We are applying a force to this bowling ball, but the force is positive 5 newtons, isn't it? Positive 5 newtons. And positive means in this graph it means to the right, as it usually does. So this impulse is going to make the bowling ball go faster or slower. It's going to make it go faster because we're going to push on it in the direction it's already moving. So its final velocity. We're going to increase its velocity. We're going to increase its momentum. Now this force right here, for part B, it's negative 5 newtons. Now what does the negative mean? Yeah, the negative means to the left, so we're going to push on it to the left with 5 newtons for 1 second. And so we're going to change its motion. We're probably going to reduce or maybe even reverse its momentum. Reverse the direction of it anyway. I don't know. We'll see. Let's do the math. Do the math to save the world. Okay. So this is our basic idea. That if you have a net force, we're just going to call this the net force, times time, the result will be a change in momentum of the object. This is the basic equation for this problem. Well, we know what the force is, and we know what our delta t is. What does delta t mean? It means our change in time. Or you can think of it as the span of time where this force was applied. So this is 5 newtons times, now how much time was this force applied? For 1 second. Now somebody's going to accidentally put 2 seconds there, but what's the problem with that? Well, for the first second, it wasn't applying any force. The force was 0. So nothing was happening. The bowling ball was just doing what it was already doing. Then we applied 5 newtons for 1 second, and then we stopped again. So this delta t, where this force is being applied, is only 1 second. And that's going to be equal to our change in momentum. Well, 5 times 1 is 5. Now, newtons times seconds. Let's see what that is. That's, well, what is a newton? A newton is a kilogram meter per second squared, right? It's mass times acceleration, right? Those are the fundamental units for newtons. Well, we're multiplying newtons times a second. So what happens is that this second cancels with the second squared on the bottom, and you get 5 kilogram meter times meters per second. Kilograms times meters per second. Oh, look, mass times velocity. Those are the units for momentum, right? Mass times velocity is momentum. But this is a change in momentum. So this is going to be equal to P final minus P initial for the bowling ball. Now what are we looking for? We're looking for the final velocity, which is in here, right? So let's go down here. Here we have 5 kilogram meters per second is equal to, well, what's the final momentum? Well, that's the mass of the bowling ball times the final velocity of the bowling ball minus the initial momentum of, well, we know what that is, right? This was, well, the mass times the initial velocity. Well, let's just rewrite this. This is 7 kilograms times my final velocity, which I don't know. That's what I'm trying to find. Minus my initial velocity, which is the mass, which is 7 kilograms, times what? 2 meters per second. That was my initial velocity. Well, what is 7 times 2 is 14. Let's add 14 kilogram meters per second to both sides. So I'm going to add 14 kilogram meters per second to this side, and then add 14 kilogram meters per second to this side. So this goes away, and I'm left with 19 kilogram meters per second, and that's going to be equal to 7 kilograms times my final velocity. Well, divide both sides now by 7 kilograms, and we've got it. The final velocity is going to be equal to 19 divided by 7 kilograms meters per second. Notice that the kilograms will cancel out, leaving meters per second, and that's what velocity is measured in, so that's good. And you get 2.71 was your answer. Meters per second. So it is indeed moving a little bit faster, isn't it? Okay. Now for part B, I'm going to cheat a little bit because I've already done a lot of the calculations, right? Except that what's different now? Well, let's take a look at this graph. When I go force times time, here I went force times time. I had 5 newtons times 1 second. Well, what is here? Is it 5 newtons on part B? No, it's not 5. It's what? -5. -5 newtons times 1 second. So I'm going to have -5 kilogram meters per second. It's going to be equal to 7 kilograms times our final velocity. I'm just skipping this work and going right to here. Minus 14 kilogram meters per second. So now when I add 14 kilogram meters per second to both sides, I get 9 over here. Negative 5 plus 14 is 9. And that's going to be equal to 7 kilograms times our final velocity. So divide both sides by 7 kilograms. The kilograms cancels. And our final velocity is 1.29, if we round it off, meters per second. Now, this makes a lot of sense. See, we're going slower. In part B, we're going slower by the same amount that I'm going faster in part A. So, in part A, my force was in the same direction as the motion of the ball. So I added to its speed. So I'm going faster in the same direction. Here, in part B, well, this is how much I'm going to take away. This is how much momentum I'm actually going to take away through this impulse. So I'm going slower. I'm going in the same direction. It wasn't enough to make the bowling ball stop in reverse direction. It's going in the same direction, but it's going a lot slower. So that's the story here. So the big idea for this is here. If I give you a graph that has force as a function of time, the area underneath that graph, I thought I had a couple more minutes, is the impulse. The impulse is equal to the change in momentum, and you can just solve for your unknown then. That is all.